So this problem asks you to predict the major product of the dehydrohalogenation of 3-chloropentane. So 3-chloropentane is chlorine in the third position. So if you have a base like potassium hydroxide, since it's a secondary, it's going to give you elimination, and you're going to get, you have two beta positions but they're the same, therefore you're going to get a transalkene as a major product, and that's going to be 1, 2, 3, 4, 1, 2, 3, 4, 5, but that's not the right double bond. It's going to be that. So option D is the right answer. So it's a straightforward one. Okay, so identify the possible products of dehydrohalogenation of cis 1-bromo 2-methylcyclohexane. So it's always good to draw this in chair conformation and put the leaving group on the axial position. So if we call this, say, carbon atom A, this is going to be carbon atom B, and remember there's one more beta position, so that's also B. We have to make sure that the elimination happens, make sure to see whether the elimination happens from only one side or both sides are viable. So that's a hydrogen on carbon A, this is carbon A, and on carbon B you have CH3, that is cis to bromine, which means you have CH3 that is cis to bromine, and the hydrogen is trans, that is the one in fact that is perfectly antiperiplanar. But as we mentioned, this is also B, so that's, let's say this is called, let's call this B prime, B double prime, this is B double prime carbon, and this is B prime, and here's the antiperiplanar hydrogen, and that's the equatorial hydrogen. So both these can be eliminated because they're both 180 degrees to the leaving group, the bromine here, they're both anti. Therefore elimination of the B prime hydrogen will give you this product, a double bond here, this is carbon atom A, and that's a CH3, those two hydrogens are intact, so B prime elimination gives that. If you remove the B double prime hydrogen with a base, then you will get, this is carbon A, the CH3 is still there, and that's the B double prime. Okay, this is B prime. So both these are going to be formed. This is going to be the major product, of course. This is the minor product, but both of them will form. So therefore B is the right answer. Okay, that is carbon A, that is carbon A, B prime, B double prime. Okay, so B is the right answer for that. Okay, so for the next question, which carbocation would not likely undergo rearrangement? Okay, so we have to see if it's primary, secondary or tertiary, that's what it comes down to. So here 1, 2, 3, 4 with the positive charge on the second carbon. So we have a positive charge here and two methyl groups and a hydrogen here, right? This automatically is going to undergo rearrangement because a new hydrogen is going to go there. If it has already one hydrogen, then now it will have two hydrogen and the positive charge will come there. So that's going to undergo rearrangement. This again, this is also going to undergo rearrangement because this is a secondary carbon. Of course you don't have a hydrogen here, but there is going to be a methyl shift. Okay, so now you will have a methyl shift. So CH3 minus propagation, or sorry, transformation, positive charge, and the new methyl group is going to go there, and the previous hydrogen is going to still be there. Okay, so yes, it will undergo rearrangement. This one is not going to undergo rearrangement because that's already a tertiary. There is no need for it to undergo any more rearrangement, and this also is going to undergo rearrangement because we have primary carbocation and a hydrogen here, so the hydrogen will move there and you will get a tertiary butyl carbocation. So that's the right answer. If this alcohol is dehydrated, which alkene is likely to be formed in the largest quantity? So We have 1, 2, 3, 4, 5. We have pentanol. So let's redraw the structure. We have that. So as we know, concentrated sulfuric acid is very good at removing a molecule of water from alcohols, and it does that by an E1 mechanism, because the H plus from sulfuric acid is going to protonate the alcohol. So you'll get, in terms of mechanism, you'll get that. Now because there is no nucleophile, the bisulfite that comes from sulfuric acid, HSO4 minus, bisulfate I mean, is not a good nucleophile or a good base, nor is it a good base, right? Therefore it's not really going to participate in the reaction. That means this is going to leave, producing the carbocation. So you will get a secondary carbocation when the water leaves. And now since there is no hydrogen here for it to shift on this carbon, the methyl is going to undergo a shift. So what will happen is the CH3 is going to move as a CH3 minus, and you will get the methyl shift on that carbocation. So now still there is no base or nucleophile in the medium, but there is a hydrogen on this molecule to lose. So now what will happen is the electrons from the hydrogen are going to be removed, and you will get that. That is a rearranged alkene. So that is option D. That's the right answer. Okay, so which alcohol is dehydrated fastest in concentrated sulfuric acid? So as we just saw, when you have alcohols in sulfuric acid, you produce a carbocation. So we have to see which of these can produce the most stable carbocation, which is going to be the most stable intermediate. So that right off the bat is the most stable intermediate producing substrate, because it will produce the tertiary carbocation. You will produce a carbocation on that carbon, because that is going to be protonated and lost. Okay, whereas this one produces a primary, this one produces a secondary. Of course it will undergo rearrangement, that's a different story, but to produce this secondary itself is going to take a higher energy of activation. So if you look at that for the first reaction, the third reaction is going to look like that, and then it will undergo rearrangement to give you a tertiary carbocation. So even though it can produce a tertiary carbocation, that is going to be only possible after rearrangement, which is going to have after the alcohol leaving from a secondary carbon that produces a secondary carbocation, and therefore this is going to have a higher energy of activation, making this slower than the first one. Here again it's a primary, so it is same as B. That reaction is not going to really be that fast. So A is the right answer. So which of these reactions is going to be faster compared to the others? That's what we are going to look at. So this is SN2 reaction, and this is the methyl sulfide nucleophile and DM as a solvent. But since it's given already as an SN2, you don't really have to worry about the solvent. It's an SN2 reaction with methyl sulfide as a nucleophile with 3 different substrates. Since it's an SN2 reaction, primary is going to be the fastest, secondary is going to be the next fastest, and tertiary is going to be the slowest, because it is going to have the most steric hindrance, least steric hindrance, and intermediary steric hindrance. So 2, 3, 1, that's going to be the right answer. 2, 3, 1. So which reaction is best suited for preparation of the ether? So this ether is tertiary butyl ethyl ether. So let's look at reaction 1. If you start with reaction 1, you have tertiary butyl bromide and sodium or potassium ethoxide. So same as sodium ethoxide, except the counter cation is different. So this might give you this product, because this might act as a nucleophile substitute for the bromine to leave by an SN2 mechanism. But more than the SN2, you are going to see E2 mechanism, because when you have a tertiary substrate, a base nucleophile species is going to react primarily as a base. Therefore you will have an E2 mechanism leading to the formation of the alkene. You will make this alkene. Sorry for scribbling. So you'll make the 2-methylpropene as the major product. This is going to be simply a minor product. Okay. Therefore this reaction is not necessarily the best reaction. So let's look at the other options. So here if you look at this, CH3 CH2 MgBr, that's the negative charge. This is 2 plus 1 minus. So overall this has one positive charge, this has one negative charge. So this is the nucleophile, but this species here doesn't have a leaving group, so this reaction won't work. This reaction will work. Okay, if you look at this, you switch the anion and the leaving group, or the nucleophile and the leaving group. So you have potassium tertiary butoxide and bromoethane. So primary alkyl halide, species that can act as a nucleophile and a base, or a base, and since it's a primary leaving group, primary carbon with a leaving group, this is going to act as a nucleophile more than it would act as a base. Therefore this reaction will work wonderfully. So that will be the right answer. And here also same story, carbon negative charge, magnesium bromide, 2 plus 1 minus, overall 1 positive charge, but there is no leaving group here. Okay, so therefore this reaction is not going to work either. So C is the only right answer, and this is going to react by an SN2 mechanism. Okay, which is the weakest nucleophile here? So weakest nucleophile, let's look at the structures. So we have sodium acetate and sodium ethoxide, and we have diethyl lithium amide, 2 lone pairs and lithium plus, and we have trifluoroethyl ethoxide, sodium trifluoroethoxide. So if you look at this, if you look at the conjugate acids, that tells you what a good nucleophile is going to be and what is not going to be a good nucleophile. Because if something is stable anion, right, that is not going to be very good nucleophile because it doesn't want to donate electrons, right? They all have oxygens, and since these electrons are conjugated, the electrons are less available for nucleophilic reactions. Therefore this is going to be the weakest nucleophile. Okay, whereas the other ones, these two are not, the electrons are not removed by conjugation, therefore they are available. Nitrogen also, the electrons are not removed by conjugation, therefore it is also available for nucleophilic reactivity. This one is going to be the weakest nucleophile. Okay, we are not comparing nucleophile versus base chemistry, we are comparing just between each of them, which is going to be the weakest nucleophile, and that is this, because it is conjugated and the electrons are less available for substitution reactions.